I am Dr. D.K. Tripathi, Assistant Professor of Physics under the Department of Basic Science and Humanities. Today we will start crystallography. Crystallography is that branch of physics in which we learn the forms and physical properties of crystalline solids. We know that there are 5 states of matter: solid, liquid, gaseous state, plasma, and Bose condensate. The solids are further classified into 2 classes: crystalline solids and non-crystalline or amorphous solids. In crystalline solids, the atoms are arranged in a periodic manner in all 3 directions, as shown in the figure. The crystalline state being the low energy state, most of the solids prefer to be in the crystalline state. This is because of the fact that energy released during the formation of ordered structure is more than that in the disordered structure. This may be understood as that in crystalline solids, the atoms or the molecules or the ions, which we are taking as the building blocks, are stacked in a regular manner in all 3 dimensions. So, a 3-dimensional pattern which may be obtained by a 3-dimensional repetition of the building block or the pattern unit will be found. When the regularity of the pattern unit extends throughout a certain piece of solid, then it can be treated for many purposes as a single crystal, and it will be called as crystal. Now we know that in this different periodic arrangement in all 3 directions is seen in the crystal. So its physical properties vary with different direction, and therefore the crystal is called as anisotropic substance. The example of the crystals are calcium carbonate, ammonium chloride, quartz. Now, non-crystalline or amorphous solid. Non-crystalline or amorphous solids are the solids in which the atoms or molecules are randomly arranged and the solid exhibits short range order. Amorphous solids are formed when the atoms do not get sufficient time to be arranged in a periodic manner, like in the glass. The periodicity is interrupted there. Most of the solids of technical interest, such as metals, ceramics, ionic salts, are not single crystal, but often consist of a large number of small crystal sections, which are called as grains of various shapes and sizes, packed to one another in a quite irregular way along the interfaces called the grain boundaries. In this type of materials, the regularity or periodicity is interrupted at the grain boundaries, though the structure may be more stable. So these materials are called polycrystalline. The size of the grain in which the structure is periodic may vary from several angstrom upwards, and when it becomes comparable to the size of the pattern unit, one can no longer speak about the crystal, since the essential feature of a crystal is its periodicity of structure. So they are called as amorphous substances. Now the example of, and they are isotropic in nature. Why? Because the physical properties of solid depends on the surrounding of the atoms, ions or molecules forming the solids. In the amorphous solids, they do not have directional properties, so they are called as isotropic substances. The example of amorphous solids are glass. So as we can say that the amorphous solids exist in more number than the crystalline solids. Let us discuss the properties of crystalline solids. A crystalline solid has definite melting point. Their geometrical shape and sizes are definite. They are anisotropic in nature. The strength of all the bonds between the ions, atoms, or molecules being the same, their chemical composition is uniform. The crystalline solids have definite color. Some of the crystalline solids are transparent in nature, but most of them are having the definite color, which is seen in the visible light. Properties of amorphous solids. So amorphous solids have no definite shape. They are isotropic in nature. Their chemical composition is not uniform as the bonds between the atoms are not of equal strength. Their melting point is not fixed due to the variation of bond strength. So let us discuss the difference between crystalline solids and an amorphous solid. The distinction between the two does not, however, depend on their external appearance or macroscopic form. Instead, they are distinguished from one another primarily by the degree of order exhibited by the arrangement of the fundamental particles, that is, atoms, molecules, ions. So, the chief differences which can be enlisted are crystals have an orderly arrangement of their constituent particles, whereas in amorphous solids, the arrangement is not ordered. The particles are randomly organized. In crystals, a specific geometrical shape uh, in, they have with definite edges, whereas in amorphous solids, uh, they do not have geometry in their they do not have fixed geometry in their shapes. Crystalline solids have a sharp melting point in which they will definitely melt, whereas amorphous solids will have a range of temperature over which it will melt. So its melting point is not definite. Crystals have a long order arrangement of their particles, whereas amorphous solids have a short order arrangement. Crystalline solids cleavage break along particular points and directions. Amorphous solids cleavage into uneven parts with ragged edges. Crystals are also known as true solids, whereas another name of amorphous solid is supercooled liquids. Space lattice or point lattice. Space lattice or point lattice is an infinite, regular, and periodic arrangement of points in all three dimensions in which every point has surroundings identical to that of every other point in the arrangement. As shown in the figure, PR and QR are the 2 points with reference to the origin O, from which if we look the lattice, it will appear or it will viewed as same. Crystal lattice. It is defined as a space lattice in which the lattice sides are occupied by atoms or group of atoms known as bases. That is, a lattice is a regular periodic arrangement of points in space that looks a net-like structure. It has the environment about any particular point, which is in every way the same as that about any other point. So all the points are connected, and we would expect by the translation operation T defined as T is equal to N1A plus N2B plus N3C. So we can say that the lattice can be thought of as generated by the translational operation T for if one point and a set of translation vectors are chosen, then the application of T with all possible values of n's will do it, of course. Now, it is very important to distinguish a lattice from the crystal structure. A lattice is a mathematical concept, whereas the crystal structure is a physical picture, and it is formed by associating identical identically with every lattice point a structure or a building unit. So we'll discuss the basis in the next part. Let us define basis. A basis is defined as a cluster of atoms, ions, or molecules identical in composition, arrangement, and orientation. Let us understand unit cell. The region of the crystal represented by the basis vectors A, B, and C, such that a translation of this region by any integral multiple of these vectors will lead to a similar region of the crystal. Now, in the figure, we are finding that A, B, and C are the basis vectors. Let us try to know that how Wigner-C's primitive unit cell can be constructed. For that, if we connect a given lattice point to all the nearby lattice points and we draw the normals at the midpoints of the lines connecting the lattice points as shown in the figure, we will find the Wigner-C's primitive cell. So, the smallest volume enclosed by the normal planes is the Wigner-C's primitive unit cell. The volume of this cell is A dot B cross C. Basis. A basis is defined as a cluster of atoms, ions, or molecules identical in composition, arrangement, and orientations. The periodic repetition of the basis in 3 dimensions forms the structure of the crystal. The 3 non-coplanar vectors A, B, C used to define a unit cell are called basis vectors. Second, we will have to discuss very important about the crystal structure, primitive unit cell. So the unit cell occupying the smallest volume in the crystal lattice is termed as the primitive unit cell. As shown in the figure, the unit cells are ABCD, A1, B1, C1, D1, A2, B2, C2, D2. So all of these are primitive unit cells. Now the next thing comes as primitive basis vectors. So the primitive basis vectors are the 3 non-coplanar vectors A, B, and C which define a primitive unit cells as shown in the diagram. Let us try to know the difference between the unit cell and the primitive cell. A unit cell, in addition to an atom at each corner, may or may not contain additional atoms or atom as shown in the figure. But a primitive cell, unit cell, contain only one atom at each corner. So we conclude that all primitive cells are unit cells, but all unit cells may or may not be primitive cells. Bravais lattice is a fundamental concept in the description of any crystalline solids, which specifies the periodic array in which the repeated units of the crystal are arranged. The units themselves may be single atoms, group of atoms, molecules, ions, but the Bravais lattice summarizes only the geometry of the underlying periodic structures, regardless of what the actual units may be. So Bravais lattice is an infinite array of discrete points with an arrangement and orientation that appears exactly the same from whichever of the points the array is viewed. The Bravais has given the concept of space lattice in 1884. We have discussed earlier that the space lattice is a mathematical concept which represents infinite number of points in space such that the arrangement of points about a given point is similar to that about any other point. There are 14 distinguishable ways in which points can be arranged in 3-dimensional space. So therefore the Bravais lattices are 14 in number as shown in the figure. And these are simple cubic, body centered cubic, face centered cubic, simple tetragonal, body centered tetragonal, simple orthorhombic, base centered orthorhombic, body centered orthorhombic, face centered orthorhombic, simple monoclinic, monoclinic, base centered monoclinic, triclinic, trigonal, hexagonal. Let us have an idea of crystal systems. All 14 types of Bravais lattice falls under 7 crystal systems. As we have discussed earlier, the primitive basis vectors A, B and C and interfacial angles alpha, beta and gamma. So on the basis of that, we will try to distinguish between the different types of crystal systems. So the first type of crystal system is cubic. Here all three lattice constants A, B and C are equal, and also the interfacial angles alpha, beta and gamma are equal to 90 degree. The most common example of this type of crystal system is sodium chloride. Next one is tetragonal. In the tetragonal system, lattice constants A and B are equal, but the third lattice constant C is not equal to any of them. And here also the interfacial angles alpha, beta and gamma all are equal to 90 degree. The example is shown in the table. Next one is orthorhombic. In the orthorhombic crystal system, all three lattice constants are having different values, but the interfacial angles are same and they are equal to 90 degree. Monoclinic. In the monoclinic crystal system, all three lattice constants are having different values and alpha and beta are equal to 90 degree, whereas gamma is not equal to 90 degree. Iron sulfate is one of the example of this type of crystal system. Next is triclinic. In the triclinic crystal system, all three lattice constants are having the different values and the interfacial angles are also not equal to 90 degree. Example is copper sulfate. Trigonal. The lattice constant of trigonal crystal system are same, equal, A equal to B equal to C, and alpha, beta and gamma is not equal to 90 degree. The example is calcium sulfate. The last type of crystal system is hexagonal, in which lattice constants A and B are equal, but C is not equal to any one of them. And the interfacial angles alpha and beta are equal and their value is 90 degree, whereas gamma equal to 120 degree. Let us discuss the various space lattices of cubic system. So the first one in this category is simple cubic or primitive cubic or cubic p-type lattice. This type of simple cubic lattice structure is a loosely packed structure. As shown in the diagram, the cells contains atoms only at the 8 corners and thus there is only one atom associated with this cell. This cubic cell is therefore also the primitive one for the simple cubic structure. Only one element, polonium, exhibits this structure below 75 degrees centigrade. The unpopularity of this structure among the elements is due to the fact that packing is very loose. There is too much vacant space there. Why the simple cubic structure concept has been taken? Just to introduce its simple geometry, because this will simplify the discussion of the complex structures greatly. Now we want to find out the number of atoms per unit cell in the simple cubic structure. So every lattice point in simple cubic lattice situated at the corner of the unit cell is shared by 8 unit cells. So its contribution to each cell will be 1 by 8. Now if this will be, then the total contribution of 8 corners of the simple cubic lattice is 1 by 8 into 8, that will be equal to 1. So for an simple cubic lattice, there is one lattice point per unit cell. Body centered cubic structure, that is BCC structure, is also a loosely bound cubic structure. It is also not closely packed structure. Here, as shown in the figure, there are 8 lattice points at the 8 corners of the unit cell, and each is a member of 8 unit cells. In addition to that, there is one lattice point at the body center. So the total number of lattice points per BCC unit cell is 1 by 8 plus 1, that is 2. In the face-centered cubic structure, in addition to the lattice points at the 8 corners, it contains lattice points at the center of each face. So there is an extra lattice point at the center of each face of the face-centered cubic structure. The example of face-centered cubic structure is copper, nickel, gold, silver. Now there are 8 lattice points at the 8 corners of the FCC lattice, and contribution of these 8 lattice points to the unit cell is 1 by 8 into 8, that is 1. There are 6 faces of the unit cell, each atom of which belongs to the 2 unit cells. So the contribution of these 6 faces, 6 lattice points to the unit cell is 1 by 2 into 6, that is 3. So the total number of lattice points per face centered cubic cell is 1 plus 3, that is 4. These are some of the references which you must pursue to know more about the topics. Thank you.